In this video for Math 94, we'll be focusing on examples from homework number 10. The examples in this video are like problems 1 through 11 in homework number 10. And the focus is on simplifying radical expressions. Let's go back to beginning algebra and let's talk a little bit about like terms. Look at this problem. 3x squared plus 5x plus 7x squared minus 3x. You probably remember that a like term means a term that has the same variable and the same exponents. So 3x squared and 7x squared are like terms. And this is like having 3 of this item and 7 of the same item. And since we're adding, we'll just add those together and get 10 of that item. So that's 10x squared. 5x and minus 3x are also like terms. In this case, you have 5 of this item, x, and 3 of this item, x. And you're subtracting, so we say 5 minus 3 is plus 2. Now, because these do not have the same variable and the same exponent, this is x squared and this is x, this cannot be simplified further, and we would say that is in simplest form. It's very similar for radicals, but we don't have variables or exponents. With radicals, we have an index. That's whether it's a square root, a cube root, a fourth root, a fifth root, whatever. And we have the radicand, the number inside. So here we have 2 times the square root of 5 plus 3 times the square root of 2 minus the square root of 5 plus 2 times the square root of 2. Like radicals are radicals that have the same index and the same radicand, the same power on the outside and the same number or combination of numbers and variables on the inside. So we have 2 square root of 5 minus square root of 5. And remember, there's a 1 here in front of this. So I have 2 of this item and 1 of this item. 2 minus 1 is 1. So we would just write 1 square root of 5, or just square root of 5. And here, square root of 2 and 2 square roots of 2. So we have 3 of this item, 2 of this item. So that's 5 square roots of 2. And these cannot be simplified further because they are not the same root and the same radicand. This is square root of 5 and this is square root of 2. So we're done right there. So what about this problem? Can you solve this problem by yourself? Why don't you pause the video and then come back to it when you're ready? Okay, I notice I have 2 square roots of 3 minus 3 square roots of 3 and 7 square root of 3. All of these items have the same root. They're all square roots, and they all have the same radicand, square root of 3. So I have 2 of these minus 3. That leaves me with negative 1 of those, plus 7 square roots of 3. And negative 1 square root of 3 plus 7 square root of 3 is 6 square root of 3, and that seems pretty straightforward. Now, it does get a little bit harder, and one of the things that we kind of have to remember is that in this case, you might look at this problem and say, look, while both of these are square roots, I don't have the same radicand, so there's nothing I can do. But think about a problem like this from your past, like 1/4 plus 6/8. You would be wrong to say, well, there's nothing I can do, or I need a common denominator. One thing you could do is take 6/8 and you could simplify it. In this case of 6/8, simplified form is 3/4. 1 plus 3/4, of course, everybody knows, is 1. The same idea here. What we could do first to our radicals is simplify them. The square root of 45 is the square root of 9 times 5. And the square root of 20 is the square root of 4 times 5. Now, remembering my rule of radicals that I can split them up across multiplication, I can write that as square root of 9 times the square root of 5. And this is the square root of 4 times the square root of 5. The square root of 9 is 3. The square root of 5 I'll just leave as is. And the square root of 4 is 2. The square root of 5 I'll just leave as is. And now if you look at this problem, which is equivalent to my original, just like 3/4 and 6/8 are equivalent, you would look at this and say, I've got 3 of these and 2 of these. That means my final answer is 5 square roots of 5. So one of the first things you should do is simplify your radicals if you can. Now, there are lots of problems that involve indexes other than 2. This one, we have 7 times the cube root of x plus 8 times the square root of x minus 11 times the cube root of x. Again, remember, like radicals mean you have to have the same index, which these do, and the same radicand. They both have square root of x in them. So 7 minus 11, well, what would that be? That would be minus 4 cube root of x. And here we have 8 square root of x. And, well, can't add those, right? Because even though they have the same radicand, they don't have the same index. I'm finished. With cube roots, again, looking at this problem, you might think there's no way to simplify them. But remember, we can simplify these radicals first before we try to add them. So we might take a look at what are the perfect cubes. You remember them? They're 1, 8, 27, 64, 125. Any of these go into 64? Well, sure, that is a perfect cube itself. It's just the cube root of 64 times the cube root of x. And what about the cube root of 27? Well, that's a perfect cube itself, the cube root of 27 times the cube root of x. And of course, the cube root of 64 is 4. And the cube root of 27 is 3. And now you look at these are completely like radicals. There's 7 cube root of x. So that's something to do with adding radicals. You must have the same index. You must have the same radicand. But remember that you possibly could simplify the problem you are given by taking out the highest power of the index you can. What about multiplication? Well, if I just wrote this problem on the board for you to do, you might think FOIL. So let's use that. Square root of x times x, that's my first, remember, is x squared. My outer is x times the square root of 2. My inner is x times the square root of 3. And my last is square root of 2 times square root of 3, which is square root of 6. Now, if you look at this problem, it looks pretty ugly, but it really can't be simplified anymore. X squared and x times the square root of 2 are not like terms because I've got a different power here than I have here. These are like terms, but unless I use my calculator, I don't know what the square root of 2 plus the square root of 3 is. And the square root of 6, while it looks like it should be able to be simplified, really can't be. So this is in simplest form. Now, some radicals, when you multiply them together, end up with special answers. Let's try this one by FOILing it out. 6 times 6 is 36. 6 times the square root of 5, that's plus 6 times the square root of 5. This is minus 6 times the square root of 5. And square root of 5 times square root of 5, or negative square root of 5 times positive square root of 5, is negative square root of 25. Now, I got my 36, but what happens to these two terms here? They are like radicals, and you notice you get 6 minus 6. That leaves you with 0. Square root of 25 is 5. 36 minus 5, of course, is 31. You notice that you may have done something like this before. This looks an awful lot like what we did with complex numbers. You might remember the problems 2 minus 3i and 2 plus 3i, and when I multiplied those two together, I ended up with a real number. Now these are already real numbers, but this answer is a whole number that doesn't include any radicals. So that's kind of interesting to note. Just like with complex numbers, we have a name for this, and that's called a conjugate. 2 plus the square root of 3, the conjugate is 2 minus the square root of 3. And minus 2 minus the square root of 5 is minus 2 plus the square root of 5. So conjugate just means change the sign in between the real number or the whole number term and the radical term. Now what happens when we multiply by a conjugate? We already saw in the first one. Let's see if you guys can do this one. Try to multiply this out by pausing the video and see what you get. Okay, I'm going to use my FOIL method again. 3 times 3 is 9. 3 times the square root of 2 right there. Minus 3 times the square root of 2. And the square root of 2 times square root of 2 is minus the square root of 4. These terms disappear. I have 3 times the square root of 2 minus 3 times the square root of 2. Those are like radicals. They disappear, and I get 9 minus the square root of 4. The square root of 4 is 2, and that gives me 7. Notice again that when I did this, I started with irrational numbers, and I now have a rational number right here. So that's something that when you multiply by a conjugate, it gets rid of that square root factor. Now, be careful, not everything is a conjugate. These are not conjugates. Let's see what happens in this case. X times x is x squared. X times the square root of 7 is minus x times the square root of 7. This one is minus x times the square root of 7. And this one is minus square root of 7 times minus square root of 7, which is plus the square root of 49. Now, if you look at this, these are like terms. Both have an x, and both have a power of 1. And in this case, because they're both square root of 7, I could say x squared minus 2x square root of 7 plus square root of 49, which is 7, and I am completely simplified. One more multiplication example, this time with cube roots, and I might suggest that we use our box method that we had before. Do you remember this? I'm going to draw a box, and in here I'm going to put x and the cube root of 2 here, and I'm going to put x squared minus x times the cube root of 2 and plus the cube root of 4. Okay, x times x squared is x cubed. X times minus x times the square root of 3, the cube root of 3, excuse me, is minus x squared times the cube root of 2. X times the cube root of 4 is x times the cube root of 4 right here. X squared times the cube root of 2 is x squared times the cube root of 2. Notice the sign here is positive. Here, you've got to be a little careful. This is minus x times the cube root of 2 times the cube root of 2. The cube root of 2 times the cube root of 2 is the cube root of 4. And this times this is the cube root of 8. Now, you notice when you add these together that these terms here on these diagonals are identical, so they're going to disappear, and you end up with x cubed plus the cube root of 8. But what's the cube root of 8? It's none other than 2. So that was a pretty difficult problem, but it shows you how some of the techniques we use with polynomials can be used to solve these problems. Another type of simplification that we use, not as much as we used to, is called rationalizing the denominator. It's a process that when I was young was very important because we didn't have calculators. And sometimes if you took a number divided by a square root, it was difficult to do this without a calculator. And you have an equivalent form that would make it a little bit easier. But these days we don't care so much about that, but we still like to talk about this process because it's useful in advanced mathematics. To rationalize the denominator means to remove the radical from the denominator. So I'm looking at this problem and I'm asking myself, what can I multiply this by so that there no longer will be a square root in a denominator? Well, since I start with a square root, if I multiply by the square root of 3, square root of 3 times square root of 3 is just 3. But I can't just go around multiplying the denominator by itself. I need to multiply the numerator too. So that's 2 times the square root of 3 over the square root of 9, and the square root of 9 is none other than 3. So this problem is said to be rationalized. Now be careful. Look at this problem. What do you think you would multiply by on top and bottom to get rid of the radical 6 on the bottom? So I'm just going to multiply by radical 6. That gives you 10 times radical 6 over 6. Now, realize, because both the 10 and the 6 are outside of the radical, and this is the times and this is multiplication, that I can reduce this to 5 radical 6 over 3. Okay, but be careful. With rationalizing, multiplying by the item in the denominator is only useful if it is a square root. If it's a cube root, that doesn't work. Notice, if I multiply by the cube root of 7 over the cube root of 7, I'll get the cube root of 49. Now notice I said cube root. The cube root of 49 is nothing special. What I want to do is I want to find a number here that will turn into one of these perfect cubes. And remember them again. That's 1, 8, 27, 64. Next one is 125, 216, 343, and so on. So I am going to multiply by the cube root of, this is 1 7. I'd like 2 more 7s, so I'm going to multiply by the cube root of 49. Now the cube root of 49 is not a whole number, but this gives you the cube root of 7 times 49, which is 343. And the cube root of 343 is none other than 7. So unlike a square root, you can't just multiply by itself. You need to think a little bit harder here. Now, what about 25? I'd like to get one of these numbers that is a perfect cube here. And you'll notice that 25 goes into 125. And 125 is 25 times 5. So I'm going to multiply the top and bottom by the cube root of 5. That gives me 5 cube root of 5 over cube root of 125. And the cube root of 125 is none other than 5. And here I can divide out the 5s, and I end up with a completely simplified answer of the cube root of 5. Now, to finish, why don't we pause the video and have you guys try this one. Start when you're ready. Okay, I'm going to multiply by the cube root of 4 and the cube root of 4. Why did I pick the cube root of 4? Again, I want one of these numbers, and the number I'd like to have is 8. 2 times 4 is 8, so that seems like a reasonable choice here. So that would be 2 cube root of 4 over cube root of 8. Cube root of 8 is 2. These divide out, and that's the cube root of 4, which is your final answer. I hope you have found this video useful.